In general, there are two groups of satellites. Geostationary. It's great. The satellites get to look at the same thing all day, every day. And near polar. These satellites move up and down all day, every day, and they cover most of the Earth. A satellite in a geostationary orbit sits at approximately 35,786 kilometers above the Earth's surface. It orbits on the equatorial plane, with the spacecraft orbiting at the same sense as the Earth. The advantages of this is it requires only one ground station for continuous coverage, and the antennas on Earth do not have to move to meet the satellite. The disadvantages of this, however, are the high launch energy requirements and the need for frequent orbital control maneuvers in order to maintain its geostationary orbit. This allows for constant photographs to be taken of a specific point on the Earth. Near-polar satellites sit at an altitude of between 400 and 1,000 kilometers above the Earth's surface, with high inclination angles of approximately 99 degrees. These satellites are sun-synchronous. This means the satellite remains fixed with respect to the Sun, with the Earth rotating underneath the satellite. Its advantages include the fact that it can almost give complete global coverage, including high latitudes. It also produces great spatial resolution. The disadvantages, however, is the repeat cycles can be long, and data can only be received when the satellite is above the horizon of the receiving station, as opposed to the geostationary satellites, where they're always at a fixed point, so therefore the receiving stations do not have to move.
From these orbiting satellites, we can collect UV and infrared images. Here are the advantages and applications of them. The UV band is wide-ranging, from between 10 and 400 nanometers. There are three different types: UVA, UVB, and UVC. UVA is the longest UV wavelength of between 320 to 395 nanometers. UVB is a mid-length UV wavelength, which is between 280 to 320 nanometers. UVC is the shortest UV wavelength of between 200 to 280 nanometers. The benefits of UV is that its absorption on the surface of material, which makes it possible to visualize surface topology that does not need light penetration. As UV contains wavelengths that are shorter than for visible light, it is easily dispersed via the surface topology of materials, which aid in determining or identifying traits of finer and smaller nature. Devices like these are very practical in pharmaceutical industry for calculating the speed of drugs breaking down for the estimation of drug bioavailability. Technologies founded on UV are broadly incorporated in water and wastewater treatment for oxidation and disinfection. The next band that will be mentioned will be the infrared band. Infrared has a shorter wavelength, as it is a kind of electromagnetic radiation consisting of wavelengths between 780 and 1000 nanometers. Near infrared has a wavelength of between 0.78 and 3 nanometers. Mid-infrared has a wavelength between 3 and 50 nanometers, and far-infrared has a wavelength between 50 and 1000 nanometers. Infrared is beneficial with its short wavelength, as this is more suitable for monitoring vegetation. Infrared has a range of applications. One of them involves thermal cameras, enabling the measuring of temperatures over wider areas, and thermal infrared measurements being sustained for greater periods of time, in comparison with point measurements with the use of thermistors or thermocouples. Thermal infrared methods were utilised for measuring water status and leaf thermal status of croplands. Further to this, infrared light contributes to monitoring geothermal systems. Whilst reflected data chiefly consists of spectral information on the surface traits of the landscape, thermal infrared data offers more spectral information of the conditions of both the subsurface and surface of the land.
We hope you enjoyed this video depicting the processes involved and applications of UV and infrared bandwidths.